Just as it's going to be a very, very interesting.
Oh, sorry.
All right, good afternoon, everybody. So I'm Bikash Lamsal from Waseda University, Japan. I'm actually from Nepal. And this is the topic of my research that we are doing. It's one of the parts, so let's talk about this. So actually, let me talk about the highlights. So there are the two main challenges that motivate our research. One is as you can see the graph that shows the construction workforce is aging while the number of younger workers continue to decline, creating a significant labor shortage in Japan. It's about Japan. And second, the current site follow-up process, because this is the follow-up process of the construction site in Japan each and every day. The construction workers have to do the inspection job. They have to make the documents, and they have to follow up. They have to give the comments, and they have to guide the workers to what to do on the site. So these are the very important part, and these take a lot of time. And these challenges highlight the need for automated and digital solution for construction site monitoring. And the key message of this slide is that an aging workforce and inefficient manual inspection create the need for autonomous technology-driven construction on site management.
Sorry, because I just wanted to interrupt for a second. You have the ability to speak very fast because your topic is very
Okay.
complicated. I would suggest
Slowly.
Yeah.
I don't want to rap, okay?
Yeah.
Okay, anyway, thank you. So, yeah, this slide introduces our proposed framework, and then we also talk about the existing indoor robotic systems that often rely on LiDAR, or you say pre-built maps or expensive infrastructures, making them difficult to deploy on construction sites. Actually, I don't believe in the very expensive LiDAR. Yeah, you can get a result, but how many of you think that it can be implemented in the real construction sites? How many of the construction industry can offer $1 million LiDAR for getting the real precision? So our solution replaced manual site patrols with an autonomous robot, and robot capture the site image. And also we have developed our own application that is called Nav and Snap, navigation and snap. So I also talk about this system. So in that system, this system will help us to take the images, and in that images we have all the information, location-based information. You have all the EXIF and metadata that you need, and those images can be used for several purposes. And also, our framework combines autonomous robotic patrols with smartphone-based localization to enable practical, low-cost, and automated construction site monitoring. So let me talk about the integration of core system elements. Here, I'm trying to combine two different processes, but we're trying to make it a single system. We're already into this research as well. So this slide presents the three core components of our proposed system. The robot operating system provides autonomous navigation using waypoint markers and PID control. The Nav and Snap application performs visual feature tracking by using AR initialization and IMU-based localization to estimate the robot's position in real time. A custom 3D printed attachment, as you can see, it securely aligns the smartphone with the robot center line, ensuring stable image capture and accurate localization. So together, these components enable autonomous navigation, precise positioning, and automatic image collection using only a standard smartphone. We are not using any external sensors. We are not using any expensive sensors on expensive devices. We are only using the things that's in the mobile, that's in the robots, or we are using the only mobile that every person carry, the smartphone. And now we're working on iPhone SE. So let me talk about the autonomous path navigation. As you have heard about, it's very difficult to get the precise location in the non-GPS environment in the construction sites. We have heard a lot of things about the indoor positioning and localization. Everybody talks about SLAM, B-SLAM, and it's not practical in case of construction site because it's changing every day. Because the environment is changing, you need to build the maps. For example, in Japan, we have the construction sites like skyscrapers that are more than 30 stories tall. They are very big, and then they are very wide. So it's very difficult to run the robot, do the patrol, create the map each and every day. It's not practical. So we need to think of something that can be used really in the construction site. So we came up with this point at first. So the one is the PID parameters were parameterized, and then the first thing is that the slide explains how we achieve stable autonomous navigation. So it ensures smooth and accurate 90-degree turn, and we implement a closed loop PID controller for the robot's rotation, and the PID parameters were optimized experimentally, and the final values of KP that was set as 0.8, and KI was 0.05, and KD was 0.02, which provide the best balance between stability and response. And as we can see in the graph below shows the tuning process, while the images demonstrate accurate rotation to the desired angle. So this controller enables reliable path following, forming the basis for accurate localization and autonomous site patrol. So what I want to show in this slide is, it ensures the stable and precise robot navigation, enabling reliable autonomous operation in an indoor construction environment. We are focusing on indoor construction environment. So this is the core architecture of our proposed system, as you can see here. The shared visual marker strategy is unlike conventional system that use separate markers for robot navigation and localization, but our approach uses the same marker for both functions. So what we are doing is, we are trying to control the robot by detecting the markers, marker-based operation, and also we are trying to navigate our nav and snap application. What nav and snap do is, it just at first it detects the marker, it finds its real position, and when you start moving with the mobile, it will have to capture the real position of your mobile. And what we are doing is, we are using the same marker for getting the first location, and then we are putting this in the robot, and the robot will be controlled by using the AR pod, and the images captured are taken autonomously, and they are put and they are pin drop in the real map, in the 2D maps. I'll also show you in the video as well. So this is the practical remote flow follow-up workflow. So what I want to show is, this process begins by simultaneously launching the nav and snap application and the robot operating system. The robot then follows a predefined patrol route, while the smartphone continuously estimates its indoor position and automatically captures site images every 3 seconds. Each image is immediately linked to its location on the digital floor plan and synchronized with the cloud. Site engineers can remotely review these images. They can identify issues and send digital instructions directly to subcontractors. Without visiting the site, after the work is completed, the robot performs another autonomous patrol to capture updated images, allowing engineers to verify the completed work remotely. And this workflow eliminates repeated site visits, manual documentation, and location mapping, making construction follow-up faster, more efficient, and fully digital. This is the video. Okay. As you can see, now I'm opening our application. This is our nav and snap application. We select the site, and then at first we detect the marker. When we detect the marker, then it will localize our position. As you can see, the markers and the maps are being downloaded by our system. And now it shows, when the marker is detected, it shows the first floor. We are in the first floor, and we just set the mobile in the robot. And this is the mobile screen, and this is the real map that we are going to move the robot. How the robot moves, we just give the instruction to the robot by the keyboard, and now it's fully autonomous. And it just detects the first marker, and it is following the instruction of the first marker. It is moving, and we have a marker in separate positions. So at this time, we can set the marker in different areas for turning right position, turning left position, going back, turning right or left. Everything can be controlled. So a little bit faster. And when the images are taken, as you can see, the position of the images are on the map. It's very precise. Yeah. And oh, sorry. I pressed it. So as you can see, the blue points in the map, these are the points. Actually, the red point, the red arrow mark is the position of the robots or marker, robot or the mobile while we move. And the blue arrow is the place where the images are taken, and the direction of the images are taken is also shown through this arrow. So when it moves to the next part, now the robots will be active and it will turn to the right side. Yeah, in this way, we can use these two applications at a time by combining together. Now we are also going to make this a simple, compact one, but now we are working on this. And also, we had done several experiments. So to evaluate the proposed system, we conducted experiments in our university, inside the building of our university. So it is a large unstructured environment similar to real construction site, and the test area was measured by 32 meters, 32 by 10 meters, and the evaluation points were placed at 0.5 meter interval to accurately assess the localization performance. For the hardware, we intentionally used the standard iPhone SE. If you know, iPhone SE is the device that have only one simple camera, and it's a cheaper one, and of course, it's very difficult to work with that cameras. And then the localization system combined visual feature tracking, IMU data, and AR markers through sensor fusion, enabling reliable positioning in GPS-denied indoor environments. And this slide compared the conventional construction inspection process with our proposed automated workflow. Traditionally, engineers must patrol the site, take photos manually, identify locations, prepare paper-based instruction, and revisit the site to verify completed work, making the process labor-intensive and time-consuming. So in our approach, the robot autonomously captures images, the smartphone automatically links them to their locations, and all data is uploaded to the cloud for remote review and task management, which eliminates the manual location confirmation, printed instruction, and must-repeated site visits while enabling the remote monitoring. The system also achieved 100% of image uploads and 100% of image location matching in both local and large-scale environment, demonstrating the reliable performance. So this slide summarizes the localization accuracy of our system. So across 64 tracking points and 3 experiments, the accumulated drift remained very low at 0.61%, 0.18%, and 0.27%, with a minimum drift of only 0.18%. So it's very precise in case of indoor positioning and localization, using only the mobile sensors. So, and this slide presents the data upload performance of our system. 100% correct match rate with 100%, both are 100%. And finally, talking about the discussion and conclusion, we developed a high-precision smartphone-based indoor localization system for GPS-free construction, monitoring, introduced a shared marker strategy that supports both robot navigation and localization correction, and also demonstrated a digital workflow that reduces a manual inspection and improves productivity. As a future work, we'll validate the system in active construction sites and quantify improvements in navigation performance, time saving, and overall workflow efficiency. And in the future, both the system will be merged, and we don't need to work on 2 different approach, but they will be merged. Yeah. So thank you for listening. If you have any query.
Very interesting presentation. So any